Thank you. So when you talk last few days, you heard about Stratum, right? So SDKLT is the SDK that Stratum used to interface to the Broadcom devices. So this is going to give you a little more detail and what went into the design of SDKLT. And then I'm going to talk about a little, because SDKLT is used as a fixed interface to a fixed function ASIC, but SDKLT is designed for not just fixed function, for a fully programmable and a language and compiler-driven architecture. So I'm going to talk a little bit about NPL. It's difficult to get through the full architecture and design of multiple layers of networking in a half-an-hour talk, but I'm going to, I'll try to do justice if we can. And we talk, if you looked at the last talk, we talked about resiliency and then scale, but at the same time, efficiency becomes very important. So while keeping those two, people expect network to be there. A network works, and scale is, you don't have a choice, it's scaling anyway. Now it is just that how do we push on the boundary of the efficiency and how to build a network stack around it. I'm going to cover a few concepts, and there are other talks you can, look at later that will go into the detail of this. So picked up from SDX Central, those guys do some good jobs. It's a very good model in terms of, what are the layers in SDN. So there is a controller. I'm going to focus only on the two layers of the network at this point. There is an infrastructure layer with some network devices, and it shows clearly why you need a high performance interface to those devices, right? So otherwise you have all this value that is locked up and you can't get to it and come back, and the relevance of it in an SDN and a controller-based world, right? And then device itself has to be efficient. Like we talked about, it's the third dimension. And then if you saw in the last few days, quite a few speakers mentioned how they had these programs, they had to compile, and the resources were not available. So having a good architecture and a design around building an efficient pipeline, efficiency in terms of resource utilization becomes very important. I have some concepts, and hopefully we can cover some of them. So when we talk about an efficient network stack, this is how I see, right? So there is a switching pipeline, there is an SDK, there is a NOS, and a controller. But in this, if you want to step back and think a little theoretically, so we have to really architect it as a system across all layers. Then if you go and design each layer and then somehow, because the interfaces match up, you just put them together, you will get an implementation, but you may have inefficiencies of that. And then layered architecture is something that we don't have to sell. Networking has been, starting from our college days, is a layered architecture. You reuse the functionality that you have at lower layers. If your lower layer or device gives you an automatic rollback on failures, use that and build it across devices at the higher layers, right? So that's the concept. And then one of the ways is to kind of align these interfaces and align the abstractions of each of these layers, right? And efficiency at each layer is obvious, but in this, right? So why on a controller based and SDN this becomes important, right? So we had to put extra effort into solving this specific problem because once you go to an SDN controller, you're not just looking at one device, you have many devices, and then you are to react fast, you need to get these loads of information from device state from everywhere. Figure out whether there is a fault in the network somewhere or whether you're trying to kind of get a state of the network and react back and then configure the whole network. So that puts a tremendous burden on the SDKs. And so we have looked at the SDK that we have. If you, some of you who are aware of Broadcom's SDKs, you might have worked on. So SDK 6 being the latest. So we have rewritten, completely re-architected SDKLT for performance, and that's something that I'm going to talk about. So two aspects, I'll just throw two numbers, and so the rate at which you can update and delete routes is twice as fast as the previous benchmark, and the packet IO is 6 times the performance. So there is certain effort put into making this efficient so that you can use in this kind of SDN environment where that becomes very important. So I want to talk about quickly, I want to give you a little bit of background of all the theory or the design architecture I'm going to talk about. SDKLT is an open source. I'm just providing a link, and this is something that you can go look at. The code exists for you to go look at a Tomahawk-based device all the way up to the register, so it's an interesting Even if you are in academia, this could be a good place where you can go read all the way to registers and learn how SDKs are built. Another thing to NPL, which basically is the language that Broadcom uses to configure and set up the pipelines of Broadcom devices. There are two subsequent talk is basically based on these two devices. Specifically, there are many of them, but Tomahawk for the SDKLT. If we get into the network pipeline and efficient design, then it is based on a Trident 4 and Jericho 2, but these are the two links I have talked about. So let's get into the SDKLT and why it is high performing, and then what is that we have done, right? What is SDKLT before we get in? So if you are used to the Broadcom's functional SDKs, you are looking at calls like how do you add a route or how do you delete a route, right? These are all functional. So SDKLT is a new approach to SDKs. So when you have a switching ASIC, if you go back many years, if I have a switching ASIC, I would give you a register spec, right? You could read, write bits and bytes, and there is a spec where that describes. That makes it very hard for who is not the designer to go through, understand, and get the original intent of the designer. So that has evolved into building an SDK where at least we built few layers so that you are not dealing with ones and zeros at the lowest level, and then you are looking at a switching device as a set of API calls, right? And this takes it to the next level where this is more, and then industry itself has moved, right? We are doing a lot more modeling and data-driven as well as automated way of doing things. So that if you see Yang modeling and all the discussion we had, and then you could take the same concept to the next level and let the device designer provide you a user view of things, right? There is always a device view of things, right? When you design device, you look at ones and zeros, but there's somebody who is using it from top down and they would like to look at it in a different way. That's where you need to separate out the physical and logical and start giving a logical view and logical interface. That's one aspect of the SDKLT. The other is because you want to do model-driven and automated way of doing things, can we give a table-driven interface to the ASIC that you have or the device you have? Can everything be looked at as a table, including your actual tables as well as some of the controls that you have, right? So and then there are multiple aspects to it, and we will get into that, right? And not only the logical view, you can also get a physical interface to that. So you will have tables that will give you that may be abstracting multiple tables into one logical table. There may be other tables which are actually giving you, which is a mapping of a physical table. So you will have the chance to operate at a logical level as well as physical access to it, right? And then the SDK itself and some of the characteristics like why asynchronous and synchronous and atomic transactions and all, I'll get into it as we go through, okay? And so we talked about logical tables, right? So here I'm showing how you could create one table where it has many entries and fields, but as far as the user is concerned, they are looking at it as a single table, but internally there are three tables and that are put together and created this logical view, right? And then that way a user of this would look at it as a layer 2 table, VLAN table and things like that, and physically there could be many more, right? And then not only the tables, like I said, the control aspect of it is also abstracted out. And once you have all these as tables, you can go back to your traditional CRUD kind of interface where you are adding, and here there is because we have transactions, it's not only create or an add or an insert, it also has a commit. Once you do a bunch of things, then you can commit, and then you will get a confirmation back. So and then you also have additional interface for a traverse. So okay, and I'm getting into when you are designing this, what are the aspects that are considered, and what are the implications basically here. So SDKLT is a data-driven. Essentially means there is a piece of code, and all the logical table descriptions are fed to it as a data, and it has a lot of advantages in automating things, right? It separates cleanly the code and data, so the code becomes much more lean and efficient, and the code becomes reusable. I don't have to sell you data-driven. We are in the model-driven world already for many years now. So, but that is a primary design change in the whole thing. Okay. And then your APIs are repeatable. There are very fewer APIs. Functional APIs start growing, whereas if you have only a table-driven APIs, you can add tables very easily, and the same thing extends naturally. And in terms of efficiency, this is the main focus of the whole SDKLT, to get into the create a good interface for flexible as well as fixed functions, ASICs for. So one of the big things is how do you kind of do the bulk read writes, because this is the efficiency, right? Whenever there is always a situation where you would want to wipe out everything you have and you want to load, and you want an interface at the lowest layers itself where they provide you that, and then they would implement it very efficiently, being very close to the endpoint. And on the packet IO side, I said there is a huge improvement from the previous previous implementations is through DMA and whatnot, right? And the other feature is you can do transactions. You can from your control plane you are doing multiple changes to your configuration, and at some point you would say this is my transaction and all of them can you combine and push it back, right? And then there is a software model in between. What I mean is you're not directly writing to the configurator, which is kind of updating your configuration, and then the lower layers are separated. Both can run at different speeds, and there is a memory modeling that is happening so that you could write at your own pace to that memory model, and then that gets bunched and gets written faster to the hardware. So these are the things that kind of led to improvement in the performance that I talked about. Yeah. And from a controller and from a higher level point of view, all the interfaces have both synchronous as well as asynchronous interface. So it becomes especially important in the SDN case in a blob or a single router with a local control plane. That was a different model. Here you could go and tell each device what they need to load and let them do what they are doing, and then asynchronously get a reply back later on what happened, if something failed, something succeeded, and you could handle and you could write your code in an event-driven fashion. So that will allow you to kind of scale to the SDN controller level. So the interfaces has both sync as well as asynchronous thing, right? On the high availability side, there is a rollback built in. There is support for warm boot and ISSU in the SDK itself. So if a transaction is committed and acknowledged that it is done, basically that can be recovered through a database. So the SDK itself provides you at the lowest level some functionality that you could use and build your higher layers on top of it, right? And then here I'm showing there are a bunch of operations coming in. If you combine them into a transaction, and you have a choice of saying whether this is atomic or non-atomic. If you say atomic, then each of them are executed. If one of them fails, the whole thing goes back, and that way you don't have to do the exception handling. And then if not, then you could also say that keep pushing as many as possible. If there is a failure, then stop and let me know that something failed. So that's kind of built in. Quality automatically comes up. I think once we move to a data-driven, model-driven world, I think the quality naturally comes because you automated. You can automate your functionality testing. You're able to automate even the performance validation and things like that. And then so there are a bunch of additional functionality that we have added where you could record what happened and you could replay those things. And this can be used to kind of sometimes build your scripts or see what happened. So it's very hard sometimes, with race conditions, something happens and you have to go back and debug and you don't know what happened. So there are many more functions at the lowest levels that are added into the SDK that will help with the debug, right? A few more things. So there is a Debug Shell. There is a C interpreter-like interface which helps you with script development, because early stages of when you are doing development of code, you're always playing around with certain commands and see what happens. So, but at the same time, all those things can be recorded, and there is a way you could take that and then make it into a script. So because like I said, there's a record and replay, you could use that for debugging, and as well as you could use the whatever is recorded as a way to script, and that can become your real code as well in your system. Visibility, when I say visibility, I think visibility of the resource utilization is very important. It can reduce a lot of exception handling code that you need to deal with, especially on because there is a memory model tables, you could query how much memory is being used on certain tables. There is a way to monitor it. You could say if there is a certain table reached this capacity, can you send me an event? So there is a monitoring built into it. There is control. You could say when you are sharing this table from multiple services, you could say that if a specific usage reaches this limit, stop adding additional entries and fail. So there are a bunch of things built into that. So that is not only visibility; it gives you both resource reservation, monitoring, and control. So it's a very powerful tool that way. And once it is data, it becomes very simple. I think the number of APIs going down is a huge simplicity, especially in your code, that there are certain pieces of code that once you write, you would want to there can be a code bloat for every piece of functionality. You have to go use APIs, whereas if you are using a table-driven, naturally you are able to reuse a lot of that code, and sometimes hides the, because at the same time, because SDKLT is hiding a lot of hardware idiosyncrasies. When you're building ASICs of this size, right now these are into tens of billions of gates, they have a tremendous amount of functionality. There is always some, not only bells and whistles that are really cool to use, but they also come with some idiosyncrasies that are little complicated and can create a lot of complexity in your code. And by creating these logical tables to hide those idiosyncrasies, it does simplify quite a bit. So on to the next. So this is basically a way of getting a good high performance interface to the device or a switching pipeline. So I'm going to give a very brief introduction to NPL. This is the language that you can use to describe pipelines, both fully flexible ASICs like Jericho 2 and Trident 4 from Broadcom. It's difficult to describe a language in few slides, but I will try to show you few areas. Again, focus is on efficiency, because how do you not only be able to describe your pipeline and then build a program, the immediate next step is very important, right? You should be able to compile these programs and be able to insert it into your hardware. It should fit, and so there's a lot of effort went into the designing of the pipeline architecture as well as language. Hopefully, I'll bring out some of those aspects. So again, I'm going to skip the motivation for the language. So this is a sample NPL program, right? It is doing a simple layer 3, fairly readable. It's a sequential. So the program construct is the only sequential part of the NPL program, because there is always a do something after something else aspect to a pipeline. So this is your pipeline essentially. And I'm going to point out few things here, right? So one is, other than the memory init to start with, you're starting your parsing with a parse begin. And then pay attention to, there is a lookup after that. That means you are able to stop the parser, do some lookups, right? When you parse a packet, you get some fields and some information from the packet. You can do some packet processing on that. You can get additional metadata, rich metadata that is again a controller driven or your runtime driven. And that will allow you to take that data and continue your parsing. So there is the hardware has a multi-stage reentrant parser that allows you to come back and continue your parsing. So the previous parser would have stopped at certain point based on the way you set up your state machine there. So this is very powerful feature. You will be able to do very interesting and very powerful functionality with that. And another thing that I'm trying to point out few things that are not typical with other languages and other platforms I have seen in the industry. So the other thing I'm pointing out here is a multi-lookup. So when you have a table, this is fairly common. If you go back, maybe even 10, 20 years ago, we always used layer 2 table for multi-lookup, right? So your MAC table has always been used to not only learn the MAC addresses as well as same thing is used to switch. And same thing happens with RPF check and your routing table. So having a common database or common table where you can look up many times and then specifying how to look up each time when you look up the same database, what is your key, and how do you handle the results differently is a very important aspect of efficiency, right? So it shows how you can look up the table twice and then it is set up. This MAC table is described somewhere else, and then you can say, hey, I want to look up, you can say, I do the lookup n over there. And then it also, it's not showing here, maybe subsequently I'll show you. I just want you to notice there is something called do layer 3 forwarding, which is something called a switching logic. This I think is again unique. See what, when you think of a pipeline, a pipeline designer, if you are somebody who design a pipeline, you know that logic is a big part of it. Logic is a first-class citizen. Typically, we are used to, from the open flow days, when you draw it on a board, you nicely see the tables, but the hidden logic, the glue that is putting these bricks together is generally not known. Few guys who are really, and it is as many gates and as much required, as complex and as functional as anything else you would see. Actually, that may have more functionality than your tables themselves. So logic is a first-class citizen in the whole flexible architecture. So you, in this language, you can write huge pieces of switching logic that we will be able to compile and put it in a flexible hardware to do what you want to do in terms of some custom logic. And I'll show you a little bit of that a little later. So that's just a high-level view of how an NPL program looks like, right? And then I'm going to skip over the data types. This is pretty typical, but one thing to point out is something called overlays, which makes, which is somewhat similar to your C union, but at a field level, this is very important in terms of bus allocation algorithms in the back end. For power users, this makes it very important. This again is a, if you are a switch pipeline designer, your view is different from how somebody who is new might write. So this is very useful if you're a power user. Here I'm showing you a logical table. We already talked about a table being looked up twice. There are a couple of things to point out here. You could have a custom key construction method here in NPL. So when you have a logical table, you could describe what your key is, okay? And then here I'm showing another example where what is the key for the lookup 0 and what is the key for the lookup 1. And you can also have conditional. So your key is not a fixed key. When people say flexible key, it is just that, oh, I could select the keys, but it is compiled and then is fixed at the compile time. Whereas this is at runtime, you could really do conditionals, and based on that, you are picking up what your key could be. And there is a way, the result handling also, there is a result handling method you can write that comes and overrides. So when we talk about logical table, there are multiple aspects to it, where this is one where you can override these methods in terms of the inputs and outputs are much more rich abstraction than what you might have seen. I talked about logic and function. I just want to give you a little bit of background of what it is. And this becomes key in terms of efficiency, and I'll show you a little later. What do you mean by logic, right? So in your program, there is always something that is not attached to a table, that is not a lookup driven. And there's quite a bit of that logic that exists. That means it's not a localized decision, it's not a localized action, right? For somebody who is used to match action table way of writing programs, right? There's a lot more that happens that is not local to that. And then, so a simple example is that you have VLAN. If you have a packet has a tag, you have a default VLAN. If the packet has a tag, you want to pick up from VLAN. So you could write some small logic. It has nothing to do with table. So if you take a match action table as a primitive and universal primitive and build all your code around it, writing this kind of logic becomes inefficient because the table as a universal primitive is very inefficient. And on the right, I'm showing another example where you are trying to decide, hey, am I going to do layer 3 forwarding? This is another piece of logic, switching logic, where you if this, if that, multicast, unicast, all that kind of stuff. I'm showing you so that the smallest code I could just to fit the slide. But imagine having 1,000 lines of such code, and that will fit. So because of the way the Trident 4 or Jericho 2 is architected, or we have architected for efficiency, we can put huge amounts of logic and then into the ASIC itself. So imagine you have a white paper where you write what your switching logic is and it can go in. So this is as a unique concept that is part of the language as well as the architecture that goes into multiple ASICs. I'm going to cover 4 or 5 of these concepts, very difficult to go through the full language. You can go to the website, I showed nplang.org and read the spec and maybe you get some more from that. This is one more efficiency construct that we have. What happens typically in a pipeline is that you would want everything to be parallel. Why not, right? You can finish everything fast and parallel means low latency and whatnot, right? So that's all very clear. So, but what happens is typically when you have these tables or, if you're writing in other language match action tables, what will happen is that you end up with some dependencies. There are many kinds of dependencies, right? So one of the things we do is we separate out the match and action. So the blocks themselves become lightweight. So the number of dependencies go down. So the number of things you can do in parallel increase when you make them into smaller blocks and not a bigger abstract block. Okay, so we disaggregate even the basic primitives into actual primitives at the lowest level. So your match action becomes match separated from action. So that allows us to do some level of parallelism. Even then what happens is when you have multiple features, right, when you have multiple services deployed at the controller level, they all get translated into multiple tables, and what they end up is that every feature is trying to decide the next port that packet should go out or on some action. That means there are multiple tables that produce the same object, right? Now how do you handle that? You could keep them as separate results. When you keep them as separate results, what happens is that you will put them on a bus and carry them on a bus for somebody to process later. And bus is the more costliest resource when we're talking about some 12.8 terabits of switching speeds, these high-speed lines that imagine going from one end of the ASIC to going to the other end to cover all that. These are the most precious resource you have, and you want to conserve them. And and that's where the resource issues that last couple of days people have talked about, right? So when you have these parallel tables producing common results that you need to resolve. So this is one construct. It's a fairly simple concept, very, very powerful though. The whole ASIC has this notion of not as a field, but have these objects, and each object carries its priority, and they naturally has a decision-making process in the pipeline, in the sense that everyone puts their objects that have their priorities, and the higher priority objects will start flowing subsequently. So you're taking decisions. So you look at your pipeline as a decision engine as much as a data processing engine, and this allows you to take multiple objects produced by parallel lookups and resolve it, and then the winner is going to the next stage. And again, you may have multiple parallel and then the decision making. So this is a how do I say, a pipeline designer view of a pipeline, right? Which sometimes is different from a controller or even an academic view of these pipelines, right? It's not just a data processing, but there is a decision engine going on. And by putting certain hardware to allow parallelism to happen and a priority-based selection of these objects essentially allows you to do more parallel things. The more parallel things you can do, you can put in more tables and you can do more into the pipeline. So your resource problems people talked about go away, okay? And just to give you a sense, right, you talk about people when you talk, hey, what is the biggest program you have seen at these high-level languages, right? So maybe 2,000, 3,000 lines. So because of all these efficiency, we can fit in tens of thousands of lines of program of a language which is almost at the same level. So that is what leads to efficiency. There's a lot more, but it will be very hard for me to kind of put that in a half an hour talk. There are other talks you can, hopefully they'll be on YouTube that you can look at and then get that. I have a full deck on the efficient pipeline. I'm going to touch on maybe 1 or 2 in the interest of time. Maybe we're already out of time, or we can. So I'm going to talk about 2, 3 concepts and I'm going to stop, and then anyone interested, you can reach out to me. So we talked about SDK and the language, and I already talked about certain efficiency, right? So one of the most important part of a efficient pipeline is the throughput, right? So one of the decisions we took, which is very important for us, if you really want high throughput, you really have to have a lot of, you need to have small things. They become nimble and you can parallelize them a lot more. So what we do is when you take a match action as a universal primitive, we disaggregate it. And by disaggregating, you have smaller stages and they get a lot more parallel and you get a lot more throughput and you get more of them also, right? The number of stages never becomes an issue. Hardware by nature always has a limit, but the amount of functionality you can put into an ASIC when you compare with some other ASICs or some other languages becomes an order of magnitude better by doing this level of disaggregation. So when you look at match action, actually the primitives are lookups, which is a separate concept from result and a process and an action, okay? And there are a few other blocks that may come in between to make it more, either them more parallel or more rich, okay? So that, capacity we already talked about, right? Having tables and looking them up multiple times and having that abstraction and being able to specify that is something that helps us a lot. Concurrency, we talked a little bit already about the strength. So this is kind of showing how that happens. You could do these things in parallel because without using the bus, because you have certain a block that would allow you to do priority. Low latency, again, we know the usual parallelization techniques. The other things that we can do, right, is the moment you are able to disaggregate, you can do something called speculative lookups. So if you marry your action to your match, you can't do that lookup unless you really want to take that action. Whereas if you are able to disaggregate, you can do lookups just for the sake of it or heck of it, right? But usually you do it because you would want to follow multiple paths. You would want to pre-compute the results so that you can take a decision much faster. It's somewhat similar to what you see in like a, not multi-threading, hyper-threading in an Intel processor in your C program. If you have an if then else, you can do both the branches, you keep moving along both the branches and the condition evaluation comes later and meanwhile you are able to proceed. Whereas if you have taken an aggregate block, that's just a disaggregation blocks, you are able to move ahead because you're not taking actions but you are moving through your lookup. So a lot more of that happens, and once you do that, your latency becomes less because you are doing a lot more things in parallel, right? And efficiency, to make the overall pipeline efficient, there are parts, there are functionalities that we are used to that can be hard coded, but we have even the hard coded bells and whistles of a traditional ASICs that we have put in like an objects around it to make it a lot more flexible. Your inputs can be flexible, your outputs can be flexible, and then they can be changed at runtime. They have usage mode so that the same thing can be used. So we've done a lot more things around even a completely hard-coded block. And so that becomes very important in terms of efficiency. Visibility, I can talk a lot about it. This itself will require a day, but I'm going to just stop at a very high level. There are counters alone. It will take a day for me to talk about. There are trace points. You can trace where you are in your pipeline at every stage. All sorts of instrumentation is all built in. Runtime is another big concept, right? So this is something that I may spend a few minutes. So at runtime, changing things is a very important aspect. There is a compile time, but there are times where you can't rewrite your program, compile and download. So number of things that you are able to do at runtime, including designing your own tables. That means at runtime you can create a new table and insert into your pipelines, right? So it's not your NPL program anymore where you have to design your tables. Even at runtime you are able to put in add tables, add routes and things like that. So a lot of things, right? And because we look at the pipeline not only as a data processing engine, it also as a decision making engine, we can change the logic completely with reprioritization. So the strength I talked about, some of that can be reprioritized. That means at this moment you think L2 access control should override layer 3, but you can change your mind at runtime. So you are not only you can add additional tables in your pipeline from a controller without changing your NPL programs, and becomes a very powerful thing, and reprioritize. So this is a huge list, and then this is as powerful as the language itself. So if you look at the functionality of runtime interface to some of these ASICs, you will find a rich set that is going to be very useful for controllers especially to go and do things, add functionality or react to certain faults at runtime and things like that. Of course, I mean, if you are able to, I mean, in terms of simplicity, I say that, if you can write your logic naturally, right? If you're like a C programmer, you just go when you're taking a decision, you just go write your program. You're not worried about what table it belongs to, and it is not a localized decision. And you're kind of making some decisions, you're taking some actions that have nothing to do with tables, so you can naturally write that, and the size of that. So doing capability is one thing. That's doing that capability at the capacity, like I said, doing a tens of thousands of lines of programs, as well as huge amount of such switching logic, and that too on a fully flexible ASIC, right? So all these things, because of, we talked about some of these aspects of what makes it efficient, and that is how you are able to put a lot more features and functionality into the ASIC, okay? And then these are the design decisions. For the record, we touched upon some of them. So the parser is a multi-stage reentrant parser. It's not a single parser. Separation of lookups from actions is a huge design decision that helps in the overall efficiency. And then, a few more that I'm going to skip, right? And I think we talk. And logic as a first-class citizen becomes very important. People don't realize how much of switching logic exists in a switching pipeline. So in a way, we are trying to kind of balance programmability, feature, capacity, and as well as concurrent features. And then the reason, in a way, we are talking about is the building blocks that you see in this are the same building blocks that are going into your SDK and SDKLT. So don't look at SDKLT as the way it is used in Stratum, which is for a fixed function interface, but SDKLT is a fully automated, auto-generated for all the abstractions that you see at an efficient device layer, then the SDK, and then it goes up onwards, okay? So, thank you.